Tonight, we're going to talk about something you interact with every single second of your life. Something that powers every thought in your brain, every heartbeat in your chest, every photon hitting your eyes right now. And we have almost no idea what it actually is. Energy. You've heard the word 1,000 times. But here's what nobody tells you. When physicists reached into the deepest levels of reality and asked what energy is actually made of, what it looks like at the bottom, what it reduces to when you strip everything away, the answer broke the model they were using. It wasn't made of anything they expected. It didn't come from anywhere obvious, and it turned out to be stranger, older, and more fundamental than matter itself. By the end of tonight, you're going to understand why the most common thing in the universe is also the most philosophically unsettling thing physics has ever encountered. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what you think you know. Energy is the ability to do work. That's the definition you learned in school, and it's not wrong. But it's also about as satisfying as describing music as vibrations in air. Technically accurate, completely useless for understanding what you're actually dealing with. When you hold a match over a candle, something happens. The wax melts. A flame appears. Light spreads outward through the room. Your hand gets warm. The candle gets shorter. All of these are the same thing. All of them are energy-changing form. And you're watching something profoundly mysterious happen while thinking it's ordinary. The first serious attempt to understand energy as a physical quantity came in the 17th century. Gottfried Wilhelm Leibniz, the German mathematician who also invented calculus independently of Newton, proposed something he called vis viva, living force. He noticed that when objects move and collide, a certain quantity is conserved, the product of mass and the square of velocity, what we now call kinetic energy. If you double the speed of an object, its kinetic energy quadruples. That squared relationship isn't arbitrary. It turns out to be embedded in the geometry of space and time itself, though nobody knew that for another 2 centuries. A few decades after Leibniz, scientists began cataloging different forms of what seemed to be the same thing: heat, motion, electricity, magnetism, light. These all appeared different on the surface, but experiments kept showing that they could be converted into each other. Heat could produce motion. Motion could produce electricity. Electricity could produce light. And crucially, the total quantity seemed to stay constant through every transformation. James Prescott Joule, a British brewer and amateur physicist working in the 1840s, was one of the key figures in establishing this. He built an apparatus where falling weights drove paddles through water, and he measured the tiny temperature increase in the water caused by the churning. He was demonstrating that mechanical work, the energy of falling masses, converted into heat with a fixed, measurable ratio. Always the same ratio. Work didn't partially become heat. It completely became heat. 1 joule of mechanical work produced exactly 1 joule of heat. Not approximately. Exactly. Within measurement, precision. By the mid-19th century, this had crystallized into one of the most important principles in all of science: the conservation of energy. Energy cannot be created or destroyed, only transformed. This was remarkable. Not because it was counterintuitive, but because it revealed something hidden, about the structure of reality. There was a quantity that the universe seemed to be tracking, keeping books on. Whatever was happening on the surface, fire burning, wheels turning, lightning striking, the total amount of this quantity never changed. The universe was conserving something, and nobody knew why. That question stayed mostly unanswered for decades, buried beneath the practical success of thermodynamics and classical mechanics. Engineers could calculate energy transformations precisely without needing to know what energy fundamentally was. The mathematics worked. The machines ran. The steam engines powered the Industrial Revolution. Factories multiplied. Cities grew. The question of what energy actually is, at its deepest level, seemed almost philosophical, irrelevant to the practical project. Then, in the early 1900s, physics changed. Twice. And neither change was expected. The first came from a problem that had been nagging at physicists since the 1890s, something called the ultraviolet catastrophe. Here's the setup. When you heat an object, it glows. A piece of iron, heated on a forge, goes from black to red to orange to yellow as the temperature rises. Every object, at any temperature above absolute zero, radiates electromagnetic energy. The hotter the object, the more it radiates, and the shorter the wavelengths, it radiates most intensely. This is why stars of different temperatures have different colors. Cool red stars are cooler. Hot blue-white stars are hotter. The sun, somewhere in between, radiates most intensely in yellow-green light. Physicists had equations describing how objects emit radiation at different frequencies, and those equations worked reasonably well at low frequencies. At the longer wavelengths, the infrared end, the math matched experiment. But when they pushed the equations toward high frequencies, toward the ultraviolet end of the spectrum and beyond, something went wrong. Dramatically wrong. The equations predicted that the amount of energy radiated at high frequencies should be infinite. Not large. Not very large. Infinite. Every warm object in the universe would be radiating infinite energy, which would mean that sitting next to a warm stove should be instantly lethal. Obviously, that wasn't happening. People sat next to stoves every day and survived. But the mathematics of classical physics insisted they should be vaporized by infinite radiation. This was the ultraviolet catastrophe, and nobody could fix it without breaking everything else. In 1900, a physicist named Max Planck found a fix. But it required him to smuggle an idea into the mathematics that he himself found deeply uncomfortable. He proposed that energy isn't continuous. It doesn't flow in smooth, unbroken streams. Instead, it comes in discrete packets, chunks, indivisible units of a fixed minimum size. He called these quanta, the plural of the Latin word for how much. If you assigned each frequency of light a minimum energy unit, and if the minimum unit grew larger as the frequency increased, then higher frequency modes would require more energy to activate at all. At room temperature, you simply wouldn't have enough thermal energy to activate the high frequency modes. They'd be frozen out, unable to participate. The infinite sums disappeared. The math fixed itself. Planck had invented quantum theory by accident while trying to solve a comparatively mundane problem about glowing objects. He wasn't trying to revolutionize physics. He was trying to make a specific equation stop predicting nonsense. And he succeeded, at the cost of proposing something that made classical physics impossible to maintain. Energy, at its most fundamental level, comes in discrete quantities. There is a smallest possible unit of energy for any given process. You cannot have half a quantum. You cannot have a third of a quantum. You get the whole thing, or you get nothing. This was radical. Classical physics treated energy as a continuous variable. Like water, you could pour in any amount. You could pour exactly 1 liter, or 2 liters, or 1.374 liters. Any amount at all. Planck was saying energy was more like coins. You can have 1 coin, or 2, or 100, but not 1.5. The value of each coin depends on the frequency of the light involved. Planck captured this in a simple equation. The energy of a quantum equals a constant, now called Planck's constant, multiplied by the frequency. That constant is extraordinarily small. 6.626 times 10 to the negative 34 joule seconds. A number so tiny that in everyday life you would never notice the discreteness. You'd never notice that you were buying energy in coin denominations rather than pouring it continuously. Because the coins are fantastically small, millions of billions of times smaller than anything you can perceive directly. But at atomic and subatomic scales, that discreteness becomes everything. Planck himself wasn't sure his idea was physically real. He thought he might have introduced a mathematical convenience, a trick that made the numbers work without necessarily reflecting how nature actually operated. He spent years trying to find a way to derive the same result without the quantum assumption. He couldn't. But he remained uncomfortable with his own discovery for most of his career. He'd opened a door he wasn't sure he wanted to walk through. It took Albert Einstein to take the idea seriously and push it further into territory that would permanently change physics. In 1905, Einstein was working as a patent clerk in Bern, Switzerland. In his spare time, he was dismantling the foundations of classical physics. That year, he published 4 papers, any one of which would have made his career. One of them explained Brownian motion, the jittery random movement of small particles in a fluid, by showing that it was caused by collisions with individual water molecules. Another introduced special relativity. A third derived E equals mc squared as a consequence of special relativity. The fourth addressed a puzzle that had sat in physics since the 1880s, the photoelectric effect. When you shine light on a metal surface, electrons are knocked out of the metal. This by itself was understood. Light is energy. Energy can free electrons. What was not understood was the detailed pattern of how it happened. Classical wave theory predicted that a brighter light should knock electrons out more forcefully. More intensity should mean more energy transferred to each electron. The longer you shone the light, the more energy would build up, and the more vigorously electrons would eventually be ejected. But that wasn't what experiments showed. At all. The energy of the individual ejected electrons depended entirely on the color of the light, not its brightness. Dim violet light ejected electrons with more energy than bright red light. Red light, below a certain frequency, produced no electrons at all, no matter how bright it was. Increasing the brightness of that red light just gave you more of nothing. Leave it on for an hour. Leave it on for a year. Not one single electron. Classical wave theory had no explanation. Einstein did. He proposed that light itself is quantized. Not just that energy comes in packets when it's emitted or absorbed, as Planck had tentatively suggested, but that light actually travels through space as discrete particles, packets of electromagnetic energy. each one carrying an energy equal to Planck's constant, multiplied by the frequency. Einstein called them light quanta. We now call them photons. The photoelectric effect made immediate sense under this model. A single photon hits a single electron. The energy of that photon depends on its frequency. High frequency means high energy. Low frequency means low energy. If the photon's energy exceeds the binding energy of the electron to the metal, the electron escapes. If it doesn't, nothing happens. The photon is absorbed. The electron gets a small kick, but it can't break free. More photons, meaning brighter light, gives you more attempts. But the energy of each individual electron that escapes depends only on what each individual photon carries. You can't accumulate partial photons. There's no way to save up half a photon's worth of energy and wait for another half to arrive. Either the photon has enough energy to free the electron, or it doesn't. This was a clean, elegant explanation. It was also disturbing, because light, which everybody knew was a wave, was now behaving like a particle. Experiments in the 19th century had proven beyond doubt that light was a wave. Thomas Young's double-slit experiment in 1801 had shown that light, passing through two narrow openings, created an interference pattern on the other side, alternating bright and dark bands. The same pattern you get when water waves pass through two openings and add together in some places and cancel in others. This was not a subtle effect. It was definitive. Light was a wave. And James Clerk Maxwell's equations, the great equations of classical electromagnetism written in the 1860s, described light as an oscillating electromagnetic field, a wave spreading outward at the speed of light. The wave picture of light was not speculation. It was confirmed by precise experiment many times over. And now Einstein was saying it was also a particle. Both things were true, at the same time, depending on how you observed it. This was the beginning of what would become one of the most productive and most deeply confusing concepts in all of physics. Wave-particle duality. The idea that quantum objects are neither purely waves nor purely particles, but something for which classical physics had no category. Something fundamentally new. Something that required a new framework to describe. It wasn't just light that behaved this way. In the early 1920s, a French physics student named Louis de Broglie turned the problem around. If waves could behave like particles, he asked, could particles behave like waves? He proposed, in his doctoral thesis, that every massive particle has an associated wavelength. The wavelength equals Planck's constant divided by the momentum of the particle. The faster the particle moves, the larger its momentum, the shorter the wavelength. His thesis committee wasn't sure what to make of it. It was elegant mathematics, but what did it mean physically? They sent a copy to Einstein, who said it looked like it might be right. The committee passed him. De Broglie was awarded the Nobel Prize in Physics in 1929. A few years after his thesis, experiments confirmed his prediction. Clinton Davison and Lester Germer at Bell Labs in the United States and George Thomson in Britain independently showed that electrons fired at a thin, crystal-produced interference patterns. The same kind of patterns you get when light waves pass through a diffraction grating. Electrons, which everyone had understood as tiny charged balls, were interfering with themselves, producing the alternating bright and dark bands of wave interference. Diffraction and interference are wave phenomena. There's no way to explain them with purely particle behavior. The electrons were behaving as waves, with a wavelength that matched de Broglie's formula exactly. The same electrons that were clearly discrete particles, with fixed charges and fixed masses, with definite deflections in magnetic fields, were also clearly waves spread out across space. Both of these things were true simultaneously, and the question of how to reconcile them drove physics into a decade of the most intense theoretical work the discipline had ever seen. Arguments at conferences, papers demolishing each other's proposals. Heisenberg, Bohr, Schrödinger, Dirac, Born, Pauli, all wrestling with the same problem. How do you build a consistent description of nature when the objects of nature refuse to be either waves or particles? The resolution came in the late 1920s through the development of quantum mechanics. And at the center of quantum mechanics was a radical reconception of what energy is and how it relates to reality. The key figure was Erwin Schrödinger. In 1926, working in Zurich, he wrote down an equation describing how quantum systems evolve over time. The Schrödinger equation. It doesn't describe where a particle is. It doesn't tell you the trajectory a particle follows through space, the way Newton's equations describe the trajectory of a cannonball. It describes a mathematical object called the wave function, a field that assigns a complex number to every point in space. The wave function contains all the information about a system that it's possible to have. And the equation describes how that wave function changes over time. When you take the square of the wave function's amplitude at any point, you get a probability. The probability of finding the particle at that location if you measure it. The particle doesn't have a definite position before measurement. It has a spread of possible positions, each with an associated probability. And measurement collapses that spread into a single definite outcome. Where the particle actually is found is genuinely random, within the constraints set by the wave function. Not random because we don't know which it will be. Random because there's no fact of the matter in advance. There's no hidden variable that determined the outcome before the measurement. The wave function is the most complete description of the system, and the wave function doesn't specify a definite location. This sounds like philosophy. It's physics, demonstrated in thousands of experiments. Bell's inequality, proven in 1964 and tested in experiments by Alain Aspect in the early 1980s, showed that you can't explain quantum mechanics by assuming particles have definite properties that we simply haven't measured. The universe really is indeterminate, really is probabilistic, at the fundamental level. And the important point for energy is what happens when you apply this framework to the concept of energy itself. In quantum mechanics, energy is not a number a particle simply has. Energy corresponds to an operator, a mathematical object that acts on the wave function. When you measure the energy of a quantum system, the wave function collapses into one of a specific set of allowed states. These states are called energy eigenstates, and only the energies corresponding to those states are available. Not a continuous range. Not any value you like. A discrete set of possible outcomes. This is where quantization stops being just a mathematical trick and becomes something deeply about the structure of reality. Energy is discrete because quantum mechanics says it must be. Because the wave equation, when you solve it for a confined system, only has solutions at specific values. Like a guitar string that can only vibrate at certain frequencies. The string has a fundamental frequency, an octave above that, a frequency a fifth above that, and so on. Only those frequencies are solutions to the wave equation for a string fixed at both ends. Any other frequency simply doesn't fit the boundary conditions. The energy levels of quantum systems are the same. Only certain values are solutions. Any other value isn't suppressed or forbidden by some external rule. It simply doesn't exist as a valid solution to the wave equation for that system. The universe isn't prohibiting those energies. They're just not solutions, not part of the language. Let's make this concrete with the simplest possible example. A hydrogen atom. One proton, one electron. In classical physics, the electron should be able to orbit the proton at any distance with any energy. The closer the orbit, the lower the energy. And classical electromagnetism predicted that an accelerating charge radiates energy. An electron in a circular orbit is constantly accelerating, always changing direction. It should therefore continuously radiate electromagnetic energy and spiral inward, losing energy gradually and continuously. A classical hydrogen atom should collapse in about 10 nanoseconds, not 10,000 years, not 10 years, 10 billionths of a second. Obviously, hydrogen atoms don't do this. You, composed largely of hydrogen and oxygen and carbon, have existed for more than 10 nanoseconds. The atoms in your body have been stable for billions of years. But classical physics said they shouldn't be. Quantum mechanics explains why they are. The electron in a hydrogen atom isn't orbiting in any classical sense. It exists as a wave function spread around the proton. The wave function only has stable solutions at certain specific energies. The ground state, the lowest possible energy, with a most probable radius of about 53 picometers. The first excited state, with more energy and a larger most probable radius. The second excited state, larger still, and so on. The electron can't exist between these levels. It can jump from one to another by absorbing or emitting a photon with exactly the energy difference between the levels. Exactly, not approximately. If you shine light on hydrogen with slightly the wrong frequency, nothing happens. The photon passes through without interacting. Only the exact right frequency, corresponding to the exact energy difference between two quantum levels, will be absorbed. This is why elements have spectral lines. Sharp, precise colors they absorb and emit. Not a continuous smear of frequencies. Not a broad band. Sharp lines. A fingerprint of discrete energy levels. And that fingerprint is the same for every hydrogen atom in the universe. The one in your tap water. The one in the center of the sun. The one in a galaxy 12 billion light-years away. Same levels, same spacing, same discrete structure of allowed energies. The laws of quantum mechanics are universal. They don't vary with location. They don't depend on the history of the atom. They don't change with time. Every hydrogen atom in the cosmos carries the same allowed energy structure set by the same fundamental constants. And one of those constants is Planck's constant. The same number Planck introduced to fix the blackbody radiation problem in 1900. It shows up everywhere. In atomic spectra, in chemical bonding, in nuclear structure, in the Casimir effect, in the uncertainty principle. Planck's constant is the unit of action in quantum mechanics, the fundamental quantum of nature. And every discrete energy level, in every atom, in every star, in every galaxy, is spaced by multiples of this tiny number. But quantization is only half the story. Because, even after you understand why energy comes in packets, you still haven't answered the deeper question. What is energy? What is the thing that's being quantized? Where does it live? What is it made of? In classical physics, energy was a property of matter and fields. A moving rock has kinetic energy because it's moving. A compressed spring has potential energy because of its configuration. A warm object has thermal energy because its atoms are vibrating. A charged battery has electrical potential energy because of the arrangement of charges. Energy was always attached to something. It was an attribute, a description of the state of some physical object. It wasn't a thing in itself. It was always a way of describing a thing. Quantum mechanics started to dissolve this picture. And quantum field theory, the framework that came next, replaced it with something fundamentally different. Something so different that even experienced physicists sometimes find it hard to hold in their heads. Something that changes what you think the universe is made of. Quantum field theory emerged from the marriage of quantum mechanics and special relativity in the 1930s and 40s. It became necessary when physicists tried to extend quantum mechanics to describe particles moving at nearly the speed of light. The original Schrödinger equation wasn't consistent with special relativity. It treated time differently from space, which relativity says you can't do. Space and time are woven together in relativity. You can't treat them independently. A relativistic quantum equation was needed. Paul Dirac found it in 1928. The Dirac equation describes electrons moving at any speed, up to and including close to the speed of light. It was a remarkable achievement, combining quantum mechanics with special relativity in a way that was both mathematically consistent and physically predictive. But it had an unexpected consequence. The equation had solutions corresponding to electrons with negative energy, which seemed unphysical. Electrons with negative energy? What would that mean? Dirac's interpretation was creative. He proposed that all the negative energy states were already filled, forming an invisible sea of electrons, the Dirac sea. A gap in the Dirac sea, a missing electron from one of those filled states, would appear as a positively charged object. The same mass as an electron, but opposite charge. This particle hadn't been observed. Dirac initially thought the gaps might correspond to protons, but they couldn't. The mass was wrong. Protons are almost 2,000 times heavier than electrons. In 1932, Carl Anderson discovered the positron in cosmic ray tracks in a cloud chamber. A particle exactly like the electron, but positively charged. The anti-electron. Dirac's equation had predicted it. This was the first discovery of antimatter. And it came directly from trying to reconcile quantum mechanics with special relativity. The deeper framework that could handle all of this cleanly, without the awkward picture of a Dirac sea, was quantum field theory. And its central idea changed everything about how to think about particles, energy, and the structure of reality. The core idea is this: forget particles as the fundamental objects. The fundamental objects are fields. A field is a quantity that has a value at every point in space. Temperature is a field. Every point in a room has a temperature. The wind velocity is a field. Every point in the atmosphere has a wind direction and speed. The gravitational field is a field. It assigns a direction and magnitude to every point in space. The electromagnetic field is a field. It has both an electric and a magnetic component, each a vector at every point. In quantum field theory, all fields are quantum. They don't have definite values at every point. They're described by wave functions. They fluctuate. And crucially, they fill all of space, everywhere. Not just where matter happens to be, everywhere. The electron field has a value at every point in the universe. The quark field has a value at every point. The Higgs field has a value at every point. The gluon field, the photon field, the W and Z boson fields, every field in the standard model of particle physics fills the entire universe at all times. Every field, all of space, all of time, simultaneously. Now comes the key move. Particles are not fundamental. Particles are excitations of fields. When the electron field is disturbed, when it's given a kick of energy, it produces a localized excitation that we call an electron. When the electromagnetic field is disturbed, it produces a photon. When the Higgs field is disturbed, it produces a Higgs boson. Every particle in the standard model is an excitation of its corresponding quantum field. The particle is not a thing that moves through space. It's a vibration in a field that fills all of space. The electron doesn't exist in the electron field the way a coin exists in your pocket. The electron is a ripple in the electron field, the way a water wave is a ripple on the ocean surface. The wave isn't in the ocean. The wave is the ocean doing something. The electron isn't in the electron field. The electron is the electron field doing something. This reframes energy completely. Energy, in quantum field theory, is not a property of particles. Energy is what particles are. When you add energy to a quantum field, you get a particle. When the particle is absorbed, the energy returns to the field. The particle and its energy are the same event, described from different angles. You can't separate them. The particle is the energy. The energy is the particle. This leads to something that sounds impossible until you work through the mathematics. Even when a quantum field is in its lowest possible energy state, with no particles, with nothing happening, with absolute emptiness as far as quantum mechanics is concerned, it still has energy. This is the quantum vacuum, and it doesn't mean nothing. It means the minimum, the ground state. The state you can't extract any more energy from. But that state has a non-zero energy. The Heisenberg uncertainty principle is responsible. It says that you cannot simultaneously know both the value of a field and how fast that value is changing. The more precisely you know one, the less precisely you know the other. This is the same principle that says you can't know the exact position and exact momentum of a particle simultaneously. But it applies to fields as well. It applies to everything in quantum mechanics. This is not a limitation of your measuring instruments. It's not that your detector is too clumsy or that you're disturbing the system by observing it. That was an early interpretation, now known to be wrong. It's a fundamental feature of how quantum systems work, built into the mathematical structure of the theory, confirmed by every experiment that's tested it. The consequence for the vacuum is this. If the field were truly at zero, with no fluctuations, its value and rate of change would both be exactly known. 0 and 0. Precisely, simultaneously. But the uncertainty principle forbids that level of precision. So the field must fluctuate. It must constantly be jittering away from zero. Not because anything is pushing it. Not because there are particles moving around inside it. But because the mathematics of quantum mechanics doesn't permit perfect stillness at the quantum level, these fluctuations are real. They're called vacuum fluctuations. And they carry energy. The energy of empty space. Virtual particles are one way to think about this, though the name is a little misleading. They're not particles that almost exist. They're not particles that pop into existence and then vanish before you can catch them. They're a mathematical way of describing and calculating the effects of the fluctuations in the vacuum fields. When you use the mathematical tools of quantum field theory, called Feynman diagrams, to calculate how real particles interact, you inevitably have to include diagrams involving particles that can't be directly observed. These are the virtual particles. They're not real in the same sense as the electrons and photons you detect, but their effects are real and measurable. This also isn't metaphor. It's measurable in a way that leaves no room for doubt. The Casimir effect is the clearest demonstration that the vacuum is not empty. In 1948, Hendrik Casimir was working at the Philips Research Laboratory in the Netherlands. He was studying the quantum behavior of electromagnetic fields, and he predicted that two uncharged metal plates placed extremely close together in a vacuum should attract each other. Not because of any obvious force. Not gravity, which is far too weak at small scales to explain the effect. Not static electricity, since the plates were specified to be electrically neutral. The attraction, Casimir said, would come from the quantum vacuum itself. Here's why. The space between two very close metal plates imposes boundary conditions on the electromagnetic field. Electromagnetic waves have to satisfy specific constraints at a metallic boundary. Specifically, the component of the electric field parallel to the surface must be zero at the surface. This means that only electromagnetic modes with the right wavelengths to fit between the plates can exist in that space. Only certain wavelengths fit. Wavelengths that are too long don't fit at all. But in the space outside the plates, all wavelengths of vacuum fluctuations continue to exist normally. There's no constraint on the outside. This creates an asymmetry. Inside the gap, certain vacuum fluctuation modes are excluded. They can't fit. Outside, they're present. The vacuum fluctuations outside the plates push the plates inward with more force than the fewer vacuum fluctuations inside push back. Net result: a force pushing the plates together. In 1997, Steve Lamoro at Los Alamos National Laboratory measured this force using plates separated by about 1 micrometer. That's 1/1000th of a millimeter. The measurement matched Casimir's prediction with high precision. Since then, the effect has been measured in multiple laboratories with increasing sensitivity. Modern experiments can detect Casimir forces with exquisite precision. The effect is real. It's measurable. It depends on the geometry of the space. It changes when you change the spacing between the plates. It depends on the material of the plates. It changes when you use different materials or different shapes. It's been measured for curved surfaces, for surfaces with different patterns, for superconducting materials, always consistent with the quantum field theory prediction. What the Casimir effect proves is this: the vacuum between those plates has less energy than the vacuum outside them. The geometry of space affects the energy of empty space. Empty space has energy. It has structure, and that structure can be modified by the physical arrangement of matter. The vacuum is not nothing. It is a quantum field in its ground state, and that ground state has energy, and the configuration of the space around it determines how much energy is there. This is where the story gets genuinely unsettling. If empty space has energy, the universe should be full of it. Every cubic centimeter of empty space, every region of vacuum, everywhere in the cosmos carries this ground state energy. In the early 1990s, physicists were able to do the calculation properly. When you sum up the contributions of all the quantum fields in the standard model to the energy density of the vacuum, you add up all the contributions from all the virtual particles of all the different types in the standard model. The answer you get is roughly 10 to the 113 joules per cubic meter. That's a 1, followed by 113 zeros per cubic meter. Now, here's the problem. We can actually measure the energy density of empty space directly. We can infer it from how the expansion of the universe is accelerating. In 1998, two independent teams studying distant supernovae made a discovery that came as a genuine shock. They were measuring the brightness of type Ia supernovae, which are used as standard candles in cosmology because they all have roughly the same intrinsic brightness. By comparing the apparent brightness with the expected brightness, you can determine the distance to each supernova. And by measuring the redshift of the light, you can determine how fast the universe was expanding when that supernova exploded. The teams expected to find that the expansion of the universe was slowing down. Gravity pulls matter together. A universe full of matter should be decelerating. Instead, they found the opposite. The universe is expanding faster over time. Something is pushing it outward. Something with negative pressure. Something built into the fabric of space itself. Albert Einstein had actually introduced a term into his equations of general relativity in 1917 to allow for a static universe. He called it the cosmological constant. He later abandoned it, famously calling it his greatest blunder when Edwin Hubble discovered the universe was expanding. But the 1998 supernova observations brought it back. The universe is not just expanding, it's accelerating. And the energy driving that acceleration has a measurable energy density. That measurement gives us a value of about 6.7 times 10 to the negative 10 joules per cubic meter. That's a very small number. Tiny. Almost nothing. The discrepancy between the predicted value from quantum field theory and the measured value from cosmology is approximately 120 orders of magnitude. 10 to the power of 120. This is, without exaggeration, the largest discrepancy between theory and measurement in the history of physics. Not off by a factor of 2. Not off by a factor of 1,000,000. Not off by a factor of 1,000,000,000. Off by a 1, followed by 120 zeros. Physicists call it the cosmological constant problem. Some call it the worst prediction in science, because the theory clearly captures something real. Vacuum fluctuations exist. The Casimir effect proves it. Energy is quantized and comes from field excitations. All of that is verified repeatedly in laboratories all over the world. But the total energy of the vacuum comes out catastrophically wrong when you sum it all up. Something is cancelling almost all of it. Some mechanism, completely unknown, is subtracting almost all of the predicted vacuum energy and leaving only the tiny remnant we observe. Nobody knows what that mechanism is. This is not a minor puzzle sitting at the edge of physics. This is a central, unresolved, deeply significant problem for our best theories. The Standard Model and quantum field theory, taken together, make this absurd prediction about the vacuum energy. And we cannot explain why the universe ignores it. One candidate explanation is supersymmetry. The idea that every boson, every integer spin particle, has a fermionic partner with half-integer spin, and vice versa. Bosons and fermions contribute to vacuum energy with opposite signs. Bosons push it up. Fermions push it down. If supersymmetry were exact, the positive vacuum energy contributions from bosons would be exactly cancelled by the negative contributions from their fermionic partners. The vacuum energy would be precisely zero. But the vacuum energy clearly isn't precisely zero. It's small, but non-zero. The universe is accelerating. So, if supersymmetry exists, it must be broken. The partners must have different masses from their counterparts. And if they have different masses, the cancellation is only partial. You'd still need some fine-tuning to get the vacuum energy as small as we observe. But at least it would be a mechanism. A reason for the near cancellation, even if imperfect. The problem is that we've found no evidence of supersymmetric particles at any energy scale we can probe. The Large Hadron Collider at CERN has searched for them at energies up to about 14 trillion electron volts. Nothing found. Supersymmetry isn't ruled out. The partners could exist at energies too high for the current collider to reach. But the most natural versions, the ones that would help most with the hierarchy problem and the cosmological constant, have been ruled out. Another candidate is some form of self-tuning mechanism. The vacuum energy adjusts itself dynamically, finds a minimum, some kind of scalar field, perhaps related to the Higgs field or perhaps entirely new, whose dynamics naturally drive the vacuum energy towards small values. These mechanisms exist in theoretical form, but none of them has been convincingly demonstrated. None has made a prediction that was then confirmed by observation. They remain possibilities. The cosmological constant problem sits at the intersection of quantum field theory, general relativity, and cosmology, and resists every attempt at resolution. And it's a problem specifically about the energy of empty space. About what energy is when it's not attached to any matter, when it's just there, in the fabric of space itself. Set that aside for a moment and look at the question from a completely different angle. Because there's a theorem in mathematics, proven in 1915, that gives the conservation of energy a deeper meaning than anyone had previously imagined. Emmy Noether was a German mathematician working at the University of Göttingen, one of the most gifted mathematicians of her generation. She had been barred from positions at German universities because she was a woman. She worked for years without pay, her seminars at times announced under Hilbert's name because the university refused to grant her the official right to lecture under her own. Under those circumstances, she proved one of the most beautiful theorems in all of mathematics. She showed that every continuous symmetry in the laws of physics corresponds exactly and necessarily to a conserved quantity. This sounds abstract, but the applications are immediate and profound. If the laws of physics are the same today as they were yesterday, if the experiments you run today would give the same results if you ran them tomorrow, then energy is conserved. This symmetry is called time translation symmetry. The laws of physics don't depend on when you apply them. And because of that symmetry alone, Noether proved energy must be conserved. Not because someone decided to conserve it, not because it happens to work out that way in experiments, because the mathematics demands it. If the laws of physics had a preferred moment in time, if an experiment run on Tuesday gave different results than the same experiment run on Wednesday, energy conservation would break. It would be violated. And if you ever observed an apparent violation of energy conservation, it would mean that the laws of physics were changing with time. Noether's theorem is not widely known outside physics. It deserves to be one of the most famous results in all of science. It gave conservation laws a deeper explanation. They weren't accidents. They weren't just observed patterns in data that happened to hold up. They were direct mathematical consequences of symmetries in the laws of nature. Conservation of momentum follows from the laws of physics being the same everywhere in space. Conservation of angular momentum follows from the laws of physics being the same regardless of orientation. And the conservation of energy follows from the laws of physics being the same regardless of when you apply them. The symmetry responsible for energy conservation is time symmetry. This has enormous implications. It means that energy is the conserved quantity that arises because physics is time symmetric. It is, in a meaningful sense, the thing that stays the same while time changes everything else. You can't have energy without time. Not in this sense. Energy is the response of a physical system to the passage of time. The two are deeply linked, inseparable. Two aspects of the same underlying structure. Energy is the response of a physical system to the passage of time. The two are deeply linked, inseparable. Two aspects of the same underlying structure. Before we follow energy further down into the quantum world, it's worth pausing on something that came between Planck's discovery and quantum field theory. Something that changed what we thought energy was attached to. Something that dissolved the boundary between energy and space itself. In 1905, the same year Einstein explained the photoelectric effect, he published a paper on special relativity. And in 1915, he published the general theory of relativity. These two theories changed the picture of energy in ways that are still not fully appreciated. Special relativity showed that energy and momentum are not separate independent quantities. They're components of a single, four-dimensional object, a four-vector. The energy-momentum four-vector. What you call energy and what you call momentum depend on your state of motion. Two observers moving relative to each other will disagree about how much energy a particle has and how much momentum it has. But they'll always agree on a specific combination, the invariant mass, which is the rest energy divided by the speed of light squared. The invariant mass is what's left when you factor out all the observer dependence. It's the part of the energy momentum that every observer agrees on. And for photons, the invariant mass is zero, which is why photons look like pure energy, pure momentum, with no rest mass, to every observer in every frame of reference. General relativity went further. Einstein showed that energy, All kinds of energy, not just mass, curves space-time. Not just matter. Energy. A room full of photons curves space-time. A strong electromagnetic field curves space-time. Even the energy of the gravitational field itself curves space-time. Gravity is self-gravitating. This is what makes general relativity non-linear. The source of gravity is energy momentum, and the gravitational field itself has energy. So the gravitational field is its own source. This non-linearity is what makes the mathematics of general relativity so much harder than electromagnetism. And it has a profound implication for energy conservation. In general relativity, in a universe that isn't static, energy conservation becomes complicated. When space is expanding, the energy of photons decreases. Their wavelengths stretch with the expansion. Longer wavelength means lower frequency, means lower energy per photon. The energy doesn't go anywhere obvious. It doesn't convert into another form we can easily identify. In a strict mathematical sense, energy is only well defined as a conserved quantity in spacetimes with time translation symmetry. In Noether's framework, conservation of energy requires that the laws of physics don't change with time. But an expanding universe is different at different times. Its geometry changes. And in a space-time with changing geometry, global energy conservation, in the simple sense we learned in school, doesn't hold. This isn't a failure of energy conservation. It's a subtlety in what conservation means in a dynamic space-time. In any small enough region of space-time, small enough that the expansion doesn't matter, energy is still locally conserved. Energy doesn't appear or vanish at any point. But adding up the total energy of the universe and getting a fixed number over time turns out to be frame-dependent and complicated in ways that have no classical analog. Cosmologists have different ways of handling this. Some say energy is not conserved in an expanding universe. Some say it is, but you have to include the energy of the gravitational field in a careful way. Some say the question of whether energy is conserved globally is not well posed in general relativity. All three positions are defensible. And this ambiguity is itself telling. It tells us that energy, as a concept, is not as simple as it first appears. It works perfectly in flat spacetime and in small regions of curved spacetime. But at cosmic scales, in a universe with dynamic geometry, the concept needs to be handled with care. Energy is not as universal or as simple as we first thought. It's a local concept that becomes subtle at large scales. This is another reason why a complete theory of quantum gravity, which would unify quantum mechanics with general relativity, is so important. It would tell us what energy means at the Planck scale, what energy means in a quantized spacetime, whether energy conservation holds in some fundamental sense, or whether it's an emergent feature of large-scale, flat spacetime. We don't have that theory yet. But its absence leaves the deepest questions about energy unanswered. The relationship between energy and information is another thread that's become increasingly important in modern physics. It started with a thought experiment by the 19th century Scottish physicist James Clerk Maxwell. Maxwell's demon. Maxwell imagined a tiny demon sitting at a small door between two chambers of gas. The demon watches molecules flying around and opens the door to let fast molecules pass one way and slow molecules pass the other. Over time, fast molecules accumulate in one chamber. slow molecules in the other. One chamber gets hot. The other gets cold. The demon has created a temperature difference, a usable energy source, without doing any work, which would violate the second law of thermodynamics. The second law says that entropy, a measure of disorder, always increases in a closed system. Heat doesn't spontaneously flow from cold to hot. Order doesn't spontaneously increase without an energy cost. Maxwell's demon seemed to violate this. It was a paradox that occupied physicists for decades. The resolution came in 1961 from Rolf Landauer at IBM. Landauer pointed out that the demon must record information about each molecule. Was it fast or slow? Should the door open or stay closed? To make a new measurement, the demon eventually has to erase the old one from its memory. And here's the key. Erasing information requires energy. Erasing one bit of information at temperature T requires releasing at least K times T times the natural logarithm of 2 in heat, where K is Boltzmann's constant. This is Landauer's principle, and it saves the second law. The demon does use energy. It uses it not in moving the door. It uses it in erasing the records of its measurements. Landauer's principle was experimentally confirmed in 2012. Researchers in Lyon and Stuttgart erased individual bits of information stored in a single particle and measured the heat released. It matched the prediction. Information is physical. Erasing information releases energy. This means that information and energy are connected in a deep way. The entropy of a physical system isn't just a vague measure of disorder. It's a count of the number of distinct configurations consistent with what we can observe. And the relationship between entropy and energy is set by temperature. The second law of thermodynamics, which says entropy always increases, is really saying something about information. That the universe tends towards states where we have less and less information about the exact microscopic configuration. And this connection between energy and information runs deeper in modern physics. In black hole physics, Hawking showed in 1974 that black holes emit thermal radiation. Not from the black hole itself, since nothing can escape past the event horizon, but from the vacuum near the event horizon. Quantum fluctuations near the horizon produce pairs of particles. One falls in, one escapes. The black hole loses energy. The temperature of the radiation is inversely proportional to the mass of the black hole. Smaller black holes are hotter and evaporate faster. Hawking radiation connects quantum mechanics, general relativity, and thermodynamics in a single result. It says that black holes have temperature. And having temperature means having entropy. And Jacob Bekenstein had already calculated that entropy in 1972. The entropy of a black hole is proportional to the area of its event horizon. Not the volume, the area. Each unit of area, equal to 4 Planck lengths squared, holds 1 bit of information. The entropy of a black hole is the number of bits of information encoded on its surface. This is the holographic principle. The information content of a 3-dimensional volume of space is determined by the area of its 2-dimensional boundary, not its volume. If this principle is general, it has profound implications for what energy is. If information is physical, if erasing information costs energy, if the information content of a region of space is encoded on its boundary. Then, energy and information are not separate things. They're deeply intertwined at the fundamental level. The implications are still being worked out. But they suggest that any complete answer to the question of what energy is made of will involve information in a fundamental way. Energy isn't just the ability to do work. It might be the currency in which physical information is exchanged and stored. Let's now look at one of the most direct windows we have into the quantum nature of energy. Lasers. A laser is a device for producing light in which all the photons are in the same quantum state. Same frequency, same phase, same direction, same polarization. This is called coherent light, and it requires understanding exactly how energy is quantized in atoms. The word laser is an acronym. Light amplification by stimulated emission of radiation. The stimulated emission part is what makes it work. And stimulated emission was predicted by Einstein, again, in 1917. Here's how it works. An atom can be in an excited energy state. An electron sits in a higher orbital than its ground state. If a photon of exactly the right energy, corresponding to the gap between the excited state and the ground state, comes along, it can stimulate the atom to release its energy early, before the atom would naturally decay. The stimulated emission produces a second photon, identical to the first. Same frequency, same phase, same direction. Now you have two coherent photons. Those two photons can each stimulate another emission, producing 4 photons. Then 8. Then 16. The number of coherent photons grows exponentially. This is the amplification. The light is amplified by stimulated emission, but it only works if the atoms are in a state where more of them are excited than are in the ground state. This is called population inversion. It's not the normal state of affairs. Normally, most atoms are in their ground state. To achieve population inversion, you have to pump energy into the system, push atoms into the excited state faster than they can decay, using electrical current, or another light source, or chemical reactions. This pumping requires energy, and that energy is what eventually comes out as the laser beam. The entire operation of a laser is a cascade of quantized energy transitions. Energy goes in, promoting electrons to specific energy levels. Photons of specific energies stimulate further emissions. Coherent light comes out. Every photon in the laser beam has exactly the same energy. Planck's constant multiplied by the frequency. The sharpness of a laser's frequency is a direct consequence of the sharpness of atomic energy levels, which is a direct consequence of quantization, which is a direct consequence of the wave nature of electrons, which is a direct consequence of quantum mechanics. From Planck's uncomfortable assumption in 1900 to the laser pointer on your desk, a century of physics, connected. There's another phenomenon that makes the quantum nature of energy impossible to ignore. Superconductivity. In certain materials, cooled below a critical temperature, electrical resistance drops to exactly zero. Not almost zero. Exactly zero. Current flows with no energy loss, indefinitely. A current, established in a superconducting ring in 1961, is still circulating today. No battery. No energy input. No decay. This is impossible classically. Classical physics says electrons moving through a conductor always lose energy to collisions with atoms. The resistivity might be very low, but it's never zero. Superconductivity is a quantum effect. In a superconductor, electrons form what are called Cooper pairs. Two electrons, normally repelling each other because they have the same negative charge, form a bound state at low temperatures through interactions mediated by the vibrations of the crystal lattice. The phonons. The Cooper pairs are bosons. Unlike single electrons, which are fermions and obey the Pauli exclusion principle, bosons can all occupy the same quantum state. Below the critical temperature, all the Cooper pairs condense into a single quantum state, a macroscopic quantum state, described by a single wave function for the entire piece of material, the pair wave function. This single macroscopic wave function has a definite phase, and the flow of current in the superconductor corresponds to a gradient in that phase. The energy of the current carrying state is exactly the same as the energy of the non-current carrying state, shifted by the electromagnetic field. Because the entire electron system is in a single quantum state, there's no mechanism for individual electrons to scatter and lose energy. They're all locked together. The current flows without resistance. Zero resistance. Zero energy loss. The superconducting state is the lowest energy state. Electrons in a regular metal can scatter off vibrations and impurities and lose energy as heat. But Cooper pairs in a superconductor can't scatter easily because doing so would require breaking the pair and ejecting it from the condensate, which costs more energy than is available at low temperatures. The energy gap in a superconductor, the minimum energy needed to break a Cooper pair, is a direct quantum mechanical quantity. It's determined by the strength of the pairing interaction. It's another discrete energy scale. Another example of the universe organizing itself around quantized energy levels. Superconductivity has become increasingly important in modern technology. Magnetic resonance imaging machines use superconducting magnets. Particle accelerators use superconducting cavities to accelerate particles. Quantum computers under development use superconducting circuits as their basic computational elements. The quantized energy states of superconducting circuits, called qubits, are the bits of quantum computation. Energy quantization, which started with Planck trying to fix a blackbody radiation formula, has ended up as the basis for the most sophisticated computing technology ever built. We should also talk about what happens to energy at the very smallest scales that any experiment has ever probed. At the Large Hadron Collider at CERN, protons are accelerated to energies of about 6.8 trillion electron volts each. Two beams traveling in opposite directions collide at 4 points around the ring. The collision energy in the center of mass frame reaches about 13.6 trillion electron volts, more than 10,000 times the rest mass energy of a proton. At these energies, the protons themselves don't survive the collision. They're torn apart. Their constituent quarks and gluons interact directly. The energy of the collision creates new particles, pairs of quarks and antiquarks, pairs of leptons and antileptons, W and Z bosons, top quarks, and, in the collisions that detected it in 2012, Higgs bosons. The energy goes in. New matter comes out. This is E equals mc squared in action. You're watching energy crystallize into mass, watching excitations in the quantum fields be created from pure kinetic energy. The collision energy becomes field excitations. Field excitations are particles. New particles with new masses exist for fractions of a second before decaying into lighter particles. Those lighter particles fly outward and are detected in the enormous detectors surrounding the collision point. From the tracks left in those detectors, physicists reconstruct what particles were created and what energies they carried. Every event is a snapshot of quantum field theory in action. Energy transactions. Field excitations. Conservation laws enforced at every step. The Large Hadron Collider has now operated for over a decade. Billions of collisions, petabytes of data, and in all of that, not a single violation of energy conservation. Not a single event where the energy in didn't match the energy out. Every measurement, consistent with quantum field theory. The universe is consistent. The laws are universal. Energy is conserved. At every scale, we've been able to probe down to distances of about 10 to the negative 19 meters, about 10,000 times smaller than a proton. The same rules hold. And yet, we know they can't be the final rules, because they don't include gravity. At the scales probed by the Large Hadron Collider, gravity is negligible. The gravitational force between two protons is about 10 to the 36 times weaker than the electromagnetic force between them. In particle physics, gravity doesn't matter. You can ignore it entirely and get extraordinarily precise answers. But at the Planck scale, 10 to the negative 35 meters, gravity becomes as strong as the other forces. At that scale, you can't ignore it. And at that scale, our current frameworks break down. Quantum field theory, applied to gravity, produces infinities that can't be removed by the mathematical techniques that work for the other forces. General relativity, applied at quantum scales, loses its foundation because it treats space-time as a smooth continuum, which can't be right at scales where quantum fluctuations become comparable to the scale itself. The incompatibility between quantum mechanics and general relativity is the deepest problem in theoretical physics. And any answer to what energy is at the most fundamental level has to confront this incompatibility. Because energy is defined in terms of time, and time is defined in general relativity as part of the geometry of space-time. And that geometry, at the Planck scale, is a quantum object, fluctuating, indefinite, uncertain. In a quantum space-time, what does it mean for time to flow? If time doesn't flow in a definite way, what does the conservation of energy mean? These are questions without current answers. But they're the right questions. The questions that any final theory of physics will have to address. What is energy when space and time are themselves quantum? Nobody knows. What we do know is this: energy is quantized. It comes in discrete packets whose size is set by Planck's constant. Energy is an excitation of quantum fields that fill all of space. Every particle is an excitation. Every interaction is an exchange of energy between fields. Empty space has energy, a ground state energy we can measure through the Casimir effect, even if we can't calculate its total value correctly. Energy and mass are the same thing. Rest mass is energy stored in the excitation structure of the fields. Energy is the conserved quantity corresponding to time symmetry, as Noether proved in 1915. It exists because the laws of physics don't change with time. Energy and information are connected at the fundamental level through Landauer's principle and the physics of black holes. And at the deepest mathematical level, energy is a spectrum of eigenvalues. The numbers you get when you apply the operator that generates time evolution to a quantum state. This is what energy is made of, as far as physics can currently reach. Not a substance, not a fluid, not a thing, a relationship, a symmetry, a mathematical structure that the universe seems to be enforcing with extraordinary precision, from the behavior of electrons in atoms to the acceleration of the expansion of the cosmos. Now, take that further into quantum mechanics. In quantum mechanics, energy and time are connected by the uncertainty principle in the same way that position and momentum are. The uncertainty in energy multiplied by the uncertainty in time must be greater than or equal to Planck's constant divided by 4 pi. This means that if you know when something happens very precisely, you know the energy very imprecisely. And if you want to measure the energy of a quantum state very precisely, you need to observe it for a long time. This is why the ground state of an atom, the lowest energy level, is perfectly sharp in principle. A stable ground state lasts forever, so you have infinite time to measure its energy. The uncertainty goes to 0. The energy is perfectly well defined. But excited states decay. They only last for finite periods before dropping back to the ground state. The shorter the lifetime, the broader the uncertainty in energy. This is called natural line width, and it's measurable. Spectral lines from short-lived excited states are broader than those from long-lived ones. Not because the measurement is imprecise, because the energy of the state itself is genuinely uncertain. The state doesn't have a single, sharply defined energy. It has a range, described by a probability distribution. The shorter the lifetime, the broader the distribution. The uncertainty principle isn't just about measurement precision. It's about what the concept of energy means for systems that don't exist forever. A state that lasts only a femtosecond, 1/4,000,000th of a second, simply doesn't have a well-defined energy in the classical sense. Its energy is smeared across a range determined by how briefly it exists. Not because we measured it clumsily, because the state itself is spread across a range of energies. Energy, at this level, isn't a property a system simply has. It's something that requires time to exist as a sharp, defined quantity. And the relationship between them is set by Planck's constant. That same number again. The fundamental quantum of action. Setting the scale of everything. Let's come back to fields, because this is where energy gets its most modern and most accurate description. In quantum field theory, the energy of a system is determined by the configuration of all the fields at every point in space. Moving particles carry kinetic energy because they're excitations of fields propagating at speed. Stationary particles carry rest energy, the famous E equals m squared, because even at rest, the field excitation that constitutes the particle has a minimum energy that can't be removed without destroying the particle itself. Rest energy is not energy stored inside a particle. It is the particle. The electron doesn't contain energy. The electron is a quantum of energy in the electron field. and the amount is determined by the mass of the electron, which is itself determined by how the electron field couples to the Higgs field. This is what the Higgs field does. It doesn't push particles around. It doesn't exert a force in the ordinary directional sense. It gives particles resistance to acceleration. Imagine the Higgs field as a medium that pervades all of space. Every particle moving through space interacts with this medium. Some particles interact strongly. They're harder to accelerate. They behave as if they have more mass. Others interact weakly. They barely notice the Higgs field. They're easy to accelerate, massless. The stronger the coupling between a particle's field and the Higgs field, the more energy is required to produce an excitation of that particle's field. The heavier the particle is. The lighter particles, like neutrinos, couple very weakly to the Higgs field. The heavier particles, like the top quark, couple very strongly. The top quark is the heaviest fundamental particle we know, with a mass of about 173 giga-electron volts, roughly 185 times heavier than a proton. Its strong coupling to the Higgs field is the reason. The photon doesn't couple to the Higgs field at all, which is why photons are massless. Why light always moves at the speed of light. Why photons can never be brought to rest. The Higgs boson, discovered at CERN in 2012, after decades of searching and the construction of the Large Hadron Collider at a cost of billions of euros, was the experimental confirmation of this mechanism. The Higgs field is real. It fills all of space. Everything moving through it couples to it to varying degrees. And that coupling is what we experience as mass. Mass is a consequence of energy. Or more precisely, mass is a type of energy. Inertial mass, the resistance to acceleration, and energy are the same thing described in different ways. This is what makes E equals mc squared so strange and so profound. The c squared isn't just a conversion factor between different units. It's telling you that mass and energy are not different substances that can sometimes be transformed into each other. They are the same thing, with different names, separated by convention and historical accident. The mass of an object is its rest energy divided by the speed of light squared. The rest energy of an object is its mass multiplied by the speed of light squared. They're the same number, looked at from different directions. Nuclear fission made this undeniable in a way that could be seen, measured, and unfortunately used as a weapon. When uranium-235 is struck by a neutron and splits into two smaller nuclei, the total mass of the products is slightly less than the total mass of the starting material. Not much less, about 0.1%. But that tiny fraction of missing mass reappears as energy. The amount is given by multiplying that missing mass by the speed of light squared. The speed of light is about 300 million meters per second. Squared, that's 90 quadrillion meters squared per second squared, or 90 quadrillion joules per kilogram. Multiply even a small missing mass by that number, and you get an enormous amount of energy. But here's what's often misunderstood about nuclear reactions. The mass didn't convert into energy. The mass was energy. The difference in binding energy between the original uranium nucleus and the product fission fragments was stored in the nuclear binding. Nuclear binding energy is what holds protons and neutrons together inside a nucleus. It comes from the strong nuclear force. When uranium splits into smaller nuclei, Those smaller nuclei happen to be more tightly bound per particle than uranium was. Less energy stored per particle in the binding. That energy difference, previously stored as binding energy in the uranium nucleus, had to go somewhere. It became kinetic energy of the flying fission fragments. And kinetic energy of billions of fragments at that scale produces the heat and radiation and pressure wave we call a nuclear explosion. Nothing was created. Nothing was destroyed. Mass and energy are the same thing. The form changed. The total amount stayed exactly the same. Noether's theorem, enforced by the time symmetry of physics, held exactly, as it always does, as it apparently always has, and apparently always will. Let's now look at what energy actually looks like when you go all the way down to the scale where quantum mechanics becomes quantum field theory, where particles stop being the right description, where fields are everything. At this level, energy doesn't look like anything. It has no color, no texture, no shape. It's not a substance you could hold or weigh or pour. It's not a fluid that flows from one place to another. It's a relationship between the state of the fields and the mathematical operator that generates time evolution, the Hamiltonian. The Hamiltonian is named after the 19th century Irish mathematician William Rowan Hamilton, who reformulated classical mechanics in a way that turned out to be perfectly suited for quantum theory a century later. The Hamiltonian is a mathematical object that represents the total energy of a system. In classical mechanics, it's a number, the sum of kinetic and potential energies. In quantum mechanics, it's an operator, a mathematical instruction for how to extract information from a wave function. When the Hamiltonian acts on the wave function of a system, it tells you how that wave function evolves from one moment to the next. The Schrödinger equation, the master equation of quantum mechanics, is literally just this. The time derivative of the wave function equals -I times the Hamiltonian acting on the wave function divided by Planck's constant. Everything in quantum mechanics flows from that equation. The dynamics, the energy levels, the allowed transitions, the response to external fields. All of it. And the eigenvalues of the Hamiltonian, the values that come out when you measure a system in an energy eigenstate, are the allowed energies. The discrete energy levels we talked about earlier. Energy, at its most fundamental, is a spectrum of numbers. The eigenvalue spectrum of the Hamiltonian. This isn't a poetic description. This isn't a metaphor for something more physical. It's the mathematical definition used in every quantum mechanics textbook on the planet. Energy is what the Hamiltonian measures. And the Hamiltonian is the generator of time evolution. So energy is what you get when you ask how a quantum system responds to the passage of time. It's not a substance. It's not a fluid. It's not a particle. It's a mathematical quantity that characterizes the relationship between a quantum system and time. Noether had it right. Energy and time are two sides of the same structure, two aspects of the same symmetry, and Planck's constant is the scale that connects them. But even accepting all of that, the question doesn't fully go away, because the fields themselves still have to come from somewhere. Why do the fields have the properties they have? Why is Planck's constant the value it is? Why is the electron's coupling to the Higgs field the value it is? Why does the electromagnetic field exist at all? Why are there 3 spatial dimensions rather than 2 or 4 or 17? Why does time run forward? Quantum field theory is extraordinary. Its predictions have been tested to more decimal places than any other theory in science. The magnetic moment of the electron is a quantity that describes how strongly an electron interacts with a magnetic field. Quantum electrodynamics predicts its value. Experiments measure it, and they agree to better than 1 part in a trillion. That's like measuring the distance from the Earth to the Moon and being accurate to less than a hair's width. No other scientific theory has achieved anything close to that level of precision. And yet, quantum field theory doesn't explain where the fields came from. It doesn't explain why the fields have the properties they have. Why the electron field couples to the electromagnetic field with precisely the charge it does. Why the Higgs field has the vacuum expectation value that gives particles the masses they have. Why space has 3 spatial dimensions. These are input parameters. Numbers you put in from experimental measurement. The theory accepts them, works brilliantly with them, but doesn't derive them from anything deeper. The standard model of particle physics, which is built on quantum field theory, has about 19 free parameters. Numbers that have to be measured and inserted rather than derived from first principles. Fine structure, constant. Quark masses. Lepton, mixing angles. The mass of the Higgs boson. The vacuum expectation value of the Higgs field. The masses of the W and Z bosons. They're just there, encoded in the fields, expressed as energy scales, determined by experiment. And we don't know why they have the values they do. Why those values and not others? We have no answer. String theory attempted to explain them. The proposal emerged from theoretical physics in the 1970s and grew into an enormous research program spanning decades. The idea was that if the fundamental objects aren't zero-dimensional point particles, but one-dimensional vibrating strings, the different vibration modes of those strings would naturally produce different particle properties, different masses, different charges, different spins. A string vibrating in its lowest mode might be a photon. A string vibrating in a higher mode might be an electron. A string vibrating in yet another mode might be a quark. Energy, in string theory, is literally the vibrational energy of strings in a higher dimensional space. All particles are the same kind of object, a string, just oscillating differently. This would unify all the particles of nature into a single type of object, and it would potentially explain the particle properties that the standard model takes as free parameters. String theory also naturally includes gravity. The graviton, the hypothetical particle that carries gravitational force, appears automatically as one of the vibration modes. This is a significant achievement. Quantum field theory has resisted, including gravity, for decades. String theory requires extra dimensions of space beyond the 3 we experience, usually 6 or 7 extra dimensions, curled up so small that we don't perceive them. Compactified, in the technical language. The shapes of these extra dimensions determine the properties of the particles we observe. Different shapes give different particle physics. The problem is that the number of possible shapes is enormous, perhaps 10 to the power of 500. Each shape corresponds to a different universe with different physical constants. This has led to the concept of the string theory landscape, a vast space of possible universes, each with different physics, of which we inhabit one. The theory has been developed with extraordinary mathematical sophistication. It's produced important results in pure mathematics. It's connected to deep ideas about black holes, information theory, and the holographic principle, which suggests that the information content of a region of space is proportional to the area of its boundary, not its volume. But it has not produced a single testable prediction that has been confirmed by experiment. Not because string theory is obviously wrong, because the strings, if they exist, vibrate at the Planck scale, about 10 to the negative 35 meters. That's roughly 20 orders of magnitude smaller than anything we can probe with current technology. The energies required to directly test string theory are so enormous that no conceivable particle accelerator built with any technology we can currently imagine would suffice. String theory remains an active research program with thousands of practitioners. It has produced remarkable mathematics. But, as an answer to what energy is made of at its deepest level, it is currently beyond our ability to test. A beautiful hypothesis. Perhaps true. Perhaps not. We can't yet say. Loop quantum gravity takes a completely different approach. Instead of starting with quantum mechanics and extending it, loop quantum gravity starts by taking general relativity seriously and quantizing space-time itself. General relativity says that gravity is not a force. It's the curvature of space-time. Mass and energy curve, the four-dimensional fabric of space and time, and objects move along the straightest possible paths through that curved fabric. What we experience as the pull of gravity is actually just following the geometry. In this view, the question of what the gravitational field is has a strange answer. The gravitational field is space-time, the geometry of the universe. Loop quantum gravity asks, if you quantize this geometry, what do you get? The result is a discrete structure. Space is not a smooth continuum. At the smallest scales, at the Planck length of 10 to the negative 35 meters, space itself is made of finite, discrete chunks. A network of interconnected nodes called a spin network. And when these networks evolve through time, they create what's called a spin foam, a discrete, granular picture of space-time itself. Energy, in this picture, isn't a continuous field spread over a smooth background. It's defined on this granular geometry. At the smallest scales, below the Planck length, space and time themselves stop being well defined. There is no smooth space. There is no smooth time. There is no energy in the usual sense. Only a quantum state of geometry that, at large scales, looks smooth and gives rise to the space and time and energy we experience. The familiar world, with its continuous fields and smoothly flowing energy, emerges from this underlying granular structure, the way the smoothness of water emerges, even though water is made of discrete molecules. Loop quantum gravity has made some predictions about the very early universe that could potentially be tested by future observations. Some models predict that the Big Bang was not the beginning, but a quantum bounce from a previous contracting universe. A universe that contracted to extreme density, at which point quantum gravitational effects became dominant, and then rebounded into the expansion we observe today. Some models predict subtle signatures in the cosmic microwave background radiation, the afterglow of the early hot universe, that would distinguish loop quantum gravity from classical general relativity. But these predictions are subtle and contested, and no observation has yet confirmed them. And loop quantum gravity and string theory remain fundamentally incompatible frameworks. They can't both be correct in their current forms. They start from different assumptions and arrive at different pictures of what space-time is. We don't know which, if either, describes reality at the Planck scale. The question of what energy is made of at the most fundamental level remains genuinely open. Not because physicists haven't thought hard about it, because the tools we have, the accelerators we've built, the telescopes we've launched, the detectors we've constructed, aren't sensitive to the scales where the answer lives. What we do know, with extraordinary precision and confidence, is what energy does. And what it does is organize reality. In the very early universe, fractions of a second after the Big Bang, temperatures were so high that the distinctions we make between different forms of energy dissolved. Photons, electrons, quarks, the Higgs field, the strong and weak, and electromagnetic forces, all were unified. Not in the sense that they were the same thing, in the sense that the symmetries distinguishing them hadn't yet broken. The universe was in a high-energy, high-symmetry state. As it expanded and cooled, those symmetries broke, a process called spontaneous symmetry breaking. At about 10 to the negative 35 seconds after the Big Bang, the strong nuclear force separated from the unified electroweak force. At about 10 to the negative 11 seconds, the electroweak force split into the electromagnetic force and the weak nuclear force, and the Higgs field settled into its current vacuum state. At about 10 to the negative 6 seconds, quarks became confined inside protons and neutrons. The energy landscape of the universe settled into its current shape, and the particles we know, with the masses they have and the interactions they undergo, crystallized out of that high-energy state. Energy, in this sense, is what the universe is made of at its most primitive. The particles we catalogue, the forces we measure, the structures we observe from atoms to galaxies, are all configurations of energy in the quantum fields that fill space-time. Different configurations, different organizations, different ways of arranging the underlying energy into structured, interacting patterns. A hydrogen atom is a particular configuration of energy in the electron field and the electromagnetic field. A star is an enormous configuration of energy in those fields, plus the strong and weak nuclear fields. A human brain is an extraordinarily complex configuration of energy in countless overlapping fields, organized by chemistry, which is organized by electromagnetism, which is organized by quantum mechanics. Everything you see is energy. Organized, configured, structured by symmetry and the laws of quantum mechanics. There's one more thread to pull. We've been talking about energy as a quantity, a number, something you measure in joules. But there's a sense in which energy is also the explanation for why things happen, why events occur in one direction in time rather than the other, why the future is different from the past. In classical mechanics, systems evolve to minimize their potential energy. A ball rolls downhill. A spring compressed by two magnets facing each other releases when you let go. Water flows from high to low. These are all energy minimization processes. In quantum mechanics, something similar happens, but with an important difference. Quantum systems don't simply minimize energy. They find the lowest energy state available to them, the ground state. But they can exist in superpositions of energy states. They can fluctuate between energy levels, and the probability of finding a system in a given energy state depends on temperature. At very low temperatures, near absolute zero, systems are almost certainly in their ground state. At higher temperatures, they're more likely to be found in excited states. This temperature dependence of energy distribution is described by the Boltzmann distribution, named after the Austrian physicist Ludwig Boltzmann. The probability of finding a system in a state with energy E at temperature T is proportional to e to the negative e divided by k times T, where k is Boltzmann's constant and e is the mathematical constant, approximately equal to 2.718. This formula appears everywhere: in chemistry, in materials science, in biology, in cosmology, in astrophysics. It describes why proteins fold the way they do, why certain chemical reactions proceed spontaneously and others don't, why the early universe had certain kinds of particles abundant and others rare, why diamonds are stable at room temperature even though graphite is lower in energy. Because the thermal energy available at room temperature isn't enough to overcome the activation barrier, energy doesn't just tell you how much is there. It tells you what's likely to happen. High energy configurations are unlikely at low temperatures and more likely at high temperatures. Transitions between energy states require specific amounts of energy, no more and no less. The structure of energy landscapes determines the structure of matter and the flow of time. A universe where energy could take any value continuously, where there were no discrete levels, would be a different kind of universe. Chemistry, as we know it, wouldn't exist, because atomic structure requires quantized energy levels. Biology, as we know it, wouldn't exist, because molecular recognition, the ability of enzymes to bind specific molecules with precision, depends on the discrete, reproducible energy structures of molecules. The specific, discrete, quantized nature of energy is not a minor technical detail. It's the reason matter has the structure it does. The reason atoms are stable for billions of years. The reason molecules form reproducibly. The reason the same amino acids assemble into the same proteins every time in every cell. The reason you're here at all. One of the strangest implications of quantum field theory is what happens when you consider forces at their most fundamental level. Push two electrons extremely close together. At short enough distances, the electromagnetic repulsion between them is enormous. In quantum field theory, what's actually happening is that virtual photons are being exchanged between the electrons. The electromagnetic force, at the quantum level, is carried by photons. Not just the real photons you can detect with a camera. Virtual photons, excitations of the electromagnetic field that exist for too short a time to be directly measured. When two electrons repel each other, they're doing it by exchanging a stream of virtual photons. Those virtual photons carry momentum. The exchange of momentum is what we experience as force. This is the quantum field theory description of force. Forces are not mysterious action at a distance, where one particle somehow reaches across space and pushes another without touching it. Forces are the exchange of particles. Field excitations being thrown back and forth between interacting particles. Electromagnetic force is exchanged photons. The weak nuclear force is exchanged W and Z bosons. The strong nuclear force is exchanged gluons. The gluons don't just carry force between quarks. They also interact with each other, which is why the strong nuclear force gets stronger at longer distances rather than weaker, and why quarks can never be found in isolation. Gravity, in quantum field theory, should be exchanged gravitons, massless particles of spin 2. Though we've never detected a graviton, and the theory of quantum gravity that would describe them remains unfinished. Every force is an exchange of energy through particles. Every interaction is an energy transaction. The universe, at its most fundamental, is a vast network of fields constantly exchanging quanta of energy with each other. The particles are the transactions. The fields are the participants. And energy is the currency being exchanged. At this point in the story, it's worth stepping back and appreciating the full picture that quantum field theory presents. Space is filled with fields. Those fields fluctuate even in their lowest energy states. Particles are quantized excitations of those fields. Energy is what those excitations carry. Forces are exchanges of energy through particle intermediaries. Mass is energy tied up in the excitation structure of the fields, mediated by the Higgs field. Antimatter is the same fields with opposite quantum numbers. The vacuum is not empty, but a sea of fluctuating field energy. And all of this emerges from a framework built in the 1940s and 50s, tested to extraordinary precision, and not contradicted by a single experiment in the 8 decades since. The Standard Model, which encodes all of this, is one of the most successful intellectual achievements in human history. Not because it's satisfying. It isn't, really. It has free parameters we can't explain. It makes a catastrophic prediction about vacuum energy. It doesn't include gravity in a consistent quantum mechanical framework. It doesn't explain dark matter, which accounts for about 27% of the energy content of the universe. It doesn't explain dark energy, which accounts for about 68%. The ordinary matter that the Standard Model so successfully describes accounts for only about 5% of the total energy content of the cosmos. The Standard Model describes 5% of what's out there, extremely accurately, but still 5%. And for the other 95%, we have names, dark matter, and dark energy, which are really just labels for our ignorance. Dark matter clusters around galaxies. We know it's there because we can see its gravitational effects. It bends light. It affects the rotation speeds of galaxies. It was present in the early universe and influenced how structures formed. But we have no confirmed particle candidate. Every detector that's looked for dark matter particles has come up empty. Dark energy is even more mysterious. It's the name we give to whatever is driving the accelerating expansion of the universe. Its energy density is what we measured and found to be incompatible with the quantum field theory prediction by 120 orders of magnitude. We know its effects precisely. We have no idea what it is. The universe has a 95% composition that our best physical theories barely address. And we don't know what that 95% is made of. Or whether, at some level, it's a form of energy we simply haven't learned to recognize yet. Let's bring this all together with one specific particle that illustrates everything we've covered. The photon. A photon is the quantum of the electromagnetic field. The fundamental unit of light. It has no mass, no charge. It travels at the speed of light in vacuum, which is the only speed it can travel at because of its zero mass. When an electron in an excited state drops to a lower energy state, the energy difference is released as a photon. The photon carries exactly the right energy, not approximately. Exactly. Planck's constant multiplied by the frequency of the light. That photon travels through space. As it does, it's not a little ball moving in a straight line. It's a quantum of the electromagnetic field, a ripple. an excitation propagating through the field at light speed. It has a probability, amplitude, spread over all of space, a wave function. As long as nobody measures it, the photon exists in a superposition of all possible paths. This is what gives rise to diffraction and interference. The photon's probability amplitude takes all routes simultaneously and interferes with itself. When the photon encounters your eye, it's absorbed by a molecule called retinal, which sits inside a protein called opsin, which sits inside a photoreceptor cell called a rod or cone in your retina. The absorption transfers the photon's energy to an electron in the retinal molecule. The electron jumps to a higher energy state. That triggers a shape change in the retinal molecule, which triggers a cascade of chemical reactions, which opens ion channels in the photoreceptor cell membrane, which changes the electrical potential across the membrane, which sends a signal along the optic nerve, which reaches the visual cortex of your brain, which produces the experience of seeing. The entire chain from emission to perception is a sequence of quantized energy transactions. Electron drops from one level to another. Photon created with exact energy. Photon absorbed by retinal molecule. Electron promoted to higher level. Molecule changes shape. Ion channel opens. Current flows. Nerve fires. Each step is a specific, discrete, quantized energy exchange. No step involves a continuous, classical energy transfer. The universe is, at every level, transacting in quanta. Even the experience of seeing, the most ordinary thing in the world, is built from billions of quantum events every second. And now, the deepest question. What is energy made of? The honest answer, the answer that physics in 2026 actually supports, is that energy is not made of anything. Not in the way that water is made of molecules. Not in the way that molecules are made of atoms. Not in the way that atoms are made of protons and neutrons and electrons. Energy is not reducible to a more fundamental ingredient. What it is, at the deepest level we can currently reach, is a mathematical structure that the universe appears to enforce with absolute consistency. A conserved quantity. A consequence of time symmetry. The eigenvalue of the Hamiltonian. The label for the excitation state of a quantum field. The currency of particle interactions. The thing you need to create matter and release when you annihilate it. These aren't different things. They're the same thing described from different angles. From the symmetry perspective, energy is what time translation invariance conserves. From the field perspective, energy is what excitations of quantum fields carry. From the measurement perspective, energy is what the Hamiltonian operator extracts from a wave function. From the cosmological perspective, energy is the quantity whose density in the vacuum we can barely calculate correctly, but can measure with precision. From the everyday perspective, energy is the candle burning, the food metabolizing, the battery discharging, the photon arriving at your eye. All the same thing, described at different scales, with different levels of precision. The deeper you look, the more abstract the description becomes, but the consistency never breaks. The same rules that govern photons in an atom govern photons in a laser that governed photons in the Big Bang. The same quantization that makes atomic spectra discrete makes nuclear energy releases precise. The same conservation law that holds in a chemical reaction, holds in a particle collider, holds in the collision of galaxy clusters billions of light years away. Energy doesn't ask permission. It doesn't make exceptions. It holds everywhere, at every scale, through every transformation, with every particle, in every corner of the observable universe. Not because nature decided to conserve it, because the laws of nature are symmetric under time translation. And symmetry, it turns out, might be the most fundamental thing of all. More fundamental than particles. More fundamental than fields. More fundamental than the specific interactions we've catalogued. The particles, the fields, the forces, the structures are all expressions of symmetry. The symmetry comes first. Everything else follows from it. Right now, in the carbon atom, sitting in the molecule of air you just inhaled, electrons are sitting in precisely quantized energy levels, refusing to occupy any energy in between. Photons are being exchanged between atoms, carrying exact energy packages, binding molecules together. The vacuum around those atoms is fluctuating, seething with ground-state energy at every point in space, producing forces we can measure and barely explain. Somewhere in those fluctuations, in that structure of fields and their excitations, in the discrete spectrum of allowed energies that quantum mechanics enforces on every system in the universe, is the answer to a question that turns out to be one of the hardest in all of science. What is energy made of? The honest answer, the answer that physics in 2026 actually supports, is that energy is made of symmetry. It's the quantity that stays constant when time flows. It's the label we give to the eigenvalues of the operator that generates that flow. It's the vibrational state of quantum fields. It's the thing that both creates and is matter. It's the ground state of empty space. It's what you get when you add excitations to a vacuum that was never truly empty. It is not made of something smaller. It doesn't reduce to a more basic ingredient. At the deepest level we can currently reach, energy is not the contents of reality. It is the structure of reality. The grammar the universe uses. The rule that holds while everything else changes. And that is not a disappointing answer. It's a remarkable one. Because it means that every time you turn on a light, every time a chemical bond forms in your body, every time a star fuses hydrogen in its core, the same mathematical symmetry that describes why time is possible at all is being enforced. Exactly, without exception, across everything. Good night.